Chapter 3.5 is about how Boolean algebra relates to computer circuits. This is based on how computers store data as binary, zeros and ones. This is true for representation of letters and numbers, as well as representing different kinds of commands that a computer can run. Have you ever seen an ASCII table before? An ASCII table stores a list of characters available to the computer, as well as a number code that represents them. So these numbers are given as codes or representations of other letters, numbers, and even computer commands that don't have a graphical representation. So if you look at the very left side, backspace is the code number 9, capital A is 65, and lowercase a is 97. These number codes are further translated into binary somewhere along the line. So, for example, A is 65, and in binary, it would be this right here, 01000001. Once we get into the assembly level, which is the lowest level of programming we can do except for programming directly in binary, we have binary representations of our commands. Here are some examples of addition, subtraction, and a branching command. And so it shows the MIPS assembly code, where MIPS is just a flavor of assembly. Add takes 3 registers, which you can think of as variables. So, variable A plus variable B equals variable C. And they'd be in a specific order, but we don't have to worry about this. This isn't assembly class. But then after those, we have the bit fields that show how the binary is laid out. So once we're writing assembly code, it has a one-to-one translation to binary, and with our higher level languages, one command may translate to several assembly commands. So everything ends up boiling down to binary electric signals. So now let's talk about logic gates. When designing circuits, some of the tools that we have are logic gates to handle AND, OR, and NOT. Using truth tables, we can see the results of A times B, which is AND, A plus B, which is OR, and A prime, which is NOT, or the negation. Now instead of using T and F like we did before, we're using zeros and ones. So for example, consider this diagram. What is the Boolean algebra expression and the truth table for it? So looking at the left side, we have our variables, and at the right side will be the final equation. So if we just look at these one gate at a time, we can build B plus C as one part, and then altogether it's A times, and then B plus C in parentheses. So what's the truth table for this diagram? Well, building out the truth table shouldn't be hard. We've been doing it so far, and it comes out to something like this. So you just have to remember that the plus sign is OR, and the dot, or any sort of multiplication, ends up being AND. Just like with our logic and set properties, we also have similar properties for Boolean algebra, so you might want to keep these in mind. For example, if we have A plus A prime, that ends up giving us 1. And A times A prime gives us 0. So note that with these rules, it is possible for two gate diagrams to be logically equivalent even if they're designed differently. Think of how this might affect the design of the physical hardware. We want the simplest design to save space and components. So let's check out an example. Show that A plus, and then B times C in parentheses, is equal to A plus B times A plus C. And we can do that with a truth table. Here's the result if we write out all the columns of the truth table, and we can see that they are logically equivalent. Here's another practice problem. Write the Boolean expression for this circuit diagram and simplify it as much as you can. And here's the solution. This all ends up boiling down to just being equivalent to A. Next is Karnaugh maps. This one gets a little long, so make sure you have enough time to watch. So Karnaugh maps are used to simplify Boolean expressions. Instead of using a truth table, we draw our expressions in a grid, and we can display all possible terms this way, and then simplify. So let's look at this. It's x and y, or x and not y. Just by looking at it, we can tell that y's value doesn't really matter, and we can just simplify this to x. But let's use a map to do it. So first, we build the grid, and we mark the two products on our grid with check marks. Once we have our check marks on the grid, we can rectangle off adjacent blocks, and we can use this to simplify. Here, our rectangle contains all states in the x row, so the simplified version here is just x. If we had multiple rectangles, then our simplified form would be the sum of these rectangles. We can also go back and verify this mathematically just by working it out. So here, try to simplify x and not y, or not x and not y. Do it with a Karnaugh map, and then build up the simplified expression. Your check marks should look like this. Your regions should look like that. And your result should be x or y based on how the entire row for x is filled and the entire column for y is filled. Sometimes when you build a map, there's just no simplification, just as with this grid. There are no adjacent blocks with check marks, so this cannot be simplified. How about when we have three variables? Well, then we build our Karnaugh map in the grid as below. Note that for the columns, the labels in each column next to each other differ by only one variable. So in other words, you can't go from yz to y'z' as neighbors. There are also some additional guidelines for us to find the simplest expression with the Karnaugh map. There are different ways to find rectangles, but they're not necessarily the most simplified forms. So there are some rules. For these maps with three variables, we're able to wrap around horizontally. So we can connect yz to y'z because these variables are only different by 1. Because we're drawing it in a 2D way, it looks like these are edges, but really you might want to think of these in 3D terms where it keeps going around horizontally. And so here's kind of a rough 3D sketch of what this might look like. Another rule is that you should choose rectangles in a way that yields the smallest number of total rectangles, and so that each rectangle is as large as possible. Also, lengths of size 3 are not allowed. Only lengths of 1, 2, or 4. So if you investigate this, if you have something of length 2 in a row, that means you're either getting all of y, or all of z prime, or all of y prime, or all of z. If you're doing it vertically, then you have x and x prime. Now, if you're only doing 3, it doesn't really cover any consistent state of some variable. And a block of 1 is allowed because that will just be whatever's left over. If we have an equation that has a missing variable from one of the terms, so for example x times y without mentioning z at all, then we can also expand this to be xyz and xyz prime, since the value of z doesn't really affect the output. But if we want to draw it on the map, we need to know what the value of z is, so this one term turns into two terms. So for an example, with this equation, if we draw it on the map and put in a rectangle, we end up filling in the entire row of x, so our resulting simplified equation is just x. This one might be a little bit harder to tell, but if we fill out the Karnaugh map and make our square, we can see that all possible states are filled for z prime, so that's the only thing that really matters. We have z prime with x and x prime, and z prime with y and y prime. So again, the only thing affecting the outcome of the entire equation is what z prime is equal to. So here's some practice. This is example 9 from the book. Simplify this following equation into the simplest form using the Karnaugh map. Your map should end up looking like this. Remember that you can wrap around horizontally. And the result will be the sum of the two products. The products are denoted by the rectangles. So we have z plus xy prime. The block of 4 ends up being z because it doesn't contain any z prime, but it does have x, x prime, y, and y prime. So that ends up just being z. The other block ends up being x, y prime, because we end up with y prime and x, and then z is the only thing that changes state. Z and z prime. And that's not all. We can also work with 4 variables. And possibly more, but we're only going to go up to 4 variables. And so each of our columns and each of our rows will have to have 2 variables each. Again, keep in mind that when you're labeling your rows and your columns, each neighboring column and or row can only differ by 1. So we have xy, xy prime, x prime y prime, and x prime y. Also, we can wrap around, and then this time it will be in both directions. So let's simplify this expression. We just need to start off by putting in our check marks. So here's the map. Here are our regions. This first block gives us x, y prime, z prime, and the second block gives us z prime, w prime. Does that make sense? So here's some practice. Build the simplest regions for this map. This is what you should end up with. Don't forget that you can wrap around in all directions. And as another practice problem, try to simplify this expression. Remember that when we have variables missing from terms, we add in those missing variables both in the normal and the prime forms. And then the regions should look like this. I use circles in this case just to make the overlaps a little bit easier to read. Okay, we're done now. We are ready to go actually work a bunch of problems, so I hope you're excited.